for this coming week. Here's what I want to do. Of course, we can vary it and we can change it a little bit depending on how it goes. But let me show you what I'm after. Today, so this is today, I want to do Mori flips and Mori flips also from diptychs. But I want to show you with examples what Mori flips are all about and well, a little bit about what they're about. And then we'll see how it goes, but Miles left two nice substantial topics from this diptych paper to go, which is the classification of diptychs, which is a pretty calculation, again using continued fractions and so on. And then, well, Miles indicated how you build one of these diptych varieties, and making that systematic and making the serial and projections work is just a little bit more work, a little bit more fun, and so I can give a sketch of the proof of that, so proof of the existence of diptychs. So these two are next week. But you know, we can certainly change that plan a little bit if when we do the exercises we find there are other things to talk about. Before I sort of really start, let me say what. Well, let me give a title. And so today I want to talk about flips and C-star actions, and at the end diptychs. You know, we're building diptychs for a purpose, not just for fun, although it is fun. Before I start, let me tell you the kind of things that I'm expecting that you already know. So, Chapter 0, I'm assuming a couple of simple things. But one, well, you know about projective space. I mean, that's obviously you know about projective space, but P2 is proj of C of x, y, z. And of course, you know formally what that means. I mean, maybe you've read Hartshorne or something. But this is a very practical calculation. This is covered by affine pieces, by affines, for instance, spec of, and now you know if you're trying to be careful about this, you write y over you write x over z and you write y over z. So this is sometimes called the open patch z uz, and of course this is isomorphic to C2. And of course you know how to do this carefully and properly and so on, and I want to do it kind of lazily and quickly, and which is approximately say that uz is the locus where z equals 1. I mean, and I'm sure you even know reasons why that's kind of very lazy and careless thing to say, but it's going to be very convenient and sort of speed up our calculations without dwelling on irrelevant points. And 2, the thing that Miles has been explaining over the past month or so is quotient singularities, so finite cyclic quotient singularities. So, for example, Z2 acts on C3, so you certainly know this, UVW mapped to minus U minus V minus W, and there's a little quotient there, so divide the quotient map here is, well, whatever it's called, it's C3 mod Z mod 3, and its spec of the invariance, W invariance, and I bet you've done the calculation, which is, well, I'll keep writing spec, but U squared, UV, V squared, UW, VW, and W squared, which, if you give these new names, you can present it much more nicely, is spec of, let me write them out, x1, x2, up to x6, those 6 generators, and now you need to, well, you will have already seen how to calculate the relations between these, the 2 by 2 minors of, let me get this right, 1, 2, 3, so x1, x3 is x2 squared, and if I put x4, x5, and x6 here, x4, x5, and then take the 2 by 2 minors of that. So this is all very easy things that, you've been doing much harder things judging by Miles's talk. But I'd just like you to I'll be using these maneuvers all the time, and I'd just like to be comfortable. These aren't the hard parts of the calculation, these are the easy parts, and so I'm just going to assume that we can recognize them when we see them. Sorry, that's very much easier than anybody really wants. So let's start more properly. So, chapter 1. I'd like to tell you what a Toric flip is. I'll slightly overstate it, but a Toric flip is a birational map between two threefolds. Is a birational map x to x plus between two threefolds which factorizes in a very particular way, which I'm just writing down so that I can tell you a whole bunch of data to do with this map, which is a whole bunch of conditions on this map, which can be written as a contraction map down to a y, and then a little kind of blow-up map out of it, where, and then a whole bunch of data. Okay, so this is a kind of forbidding long list. One, I could say this slightly more abbreviatedly, but I won't. X and x plus have q factorial terminal singularities, so are threefolds with q factorial terminal singularities. Okay, that's 1, 2. So this first map here on the left, these are two maps which I'm calling phi and phi plus. So phi is a birational morphism which contracts only finitely many lines. So phi from x to y is a birational morphism. Which contracts only finitely many lines. Only finitely many lines. So let me say C is equal to the union of some irreducible curves gamma I, such that kx times gamma I is negative for all I. So in other words, this map is an isomorphism almost everywhere, but it's contracting finite many curves on which kx is negative. 3. Well, the same for x plus with kx positive, but maybe I won't write that. Maybe I'll instead say it slightly differently. So the pcar rank, so the rank of the pcar group of X, well, so perhaps I'm assuming that these are projective to say this, but this is fine, is one more than the pcar rank of Y. Or it's perhaps better to say the relative rank. The pcar rank of X over Y is 1. And the same for X plus. Same for the pcar rank of X plus. That's 1, 2, 3, 4. Well, I said out loud that on the plus side, Kx plus is positive against contracted curves, but I could say something slightly different instead. I could say that X to X plus is not an isomorphism. Of course, there's a map here from X to X plus, a birational map, which is, these are all birational, so I can just take phi and then the inverse of phi plus. So I could put this as 5, or I could say it follows that. Phi plus also contracts finite many curves. Finitely many curves. But now Kx plus is positive on them. And in fact, if you threw all of this together, you could drop one or two parts of this. For instance, it will follow automatically that X plus has terminal singularities. There are various kind of relations among these, which I haven't really stated it quite as efficiently as I could, but that's not a problem. Hello. 3. That's a good question. X plus, good, excellent, thank you. No, very good, thank you. That's the pcar rank of X plus. So again, this relative pcar rank here is just 1. Otherwise, I could easily blow up a whole bunch of stuff on X plus and sort of destroy what I just said.
Sorry, but,
Hi. Sure, of course.
Which kind of line bond does not belong to I? Can I see this?
Say again?
Card number is less.
Very good. Yeah. Very good, yeah. So the canonical class is Q Cartier here. Well, that's part of, well, it's sort of living in this definition here. So canonical class is Q Cartier here, but it's not Q Cartier here. You've put your finger on exactly the difference. That's absolutely right.
So K, the line corresponding to Kx is not belong to Y.
That's right. That's right. He's KY is not Q Cartier. Yeah, well done. Now, the reason I spell it out in such kind of pedantic and rather slow detail is, and kind of all in one go right at the beginning, is what I really want to do today is to work out 3 examples in detail where we can see every single one of these things going on. So in the end, I want to talk about diptychs, but that will be the 3rd example. The diptychs are there to build exactly this kind of setup. But first of all, I need to do a couple of slightly simpler examples so we can see things going on and get a feel for the calculation before we dive in. So we will be actually, from now on, we'll be really getting our hands on this kind of concrete calculation. Just a little remark. So we could have defined flop, define flop similarly. And, well, the critical difference would be here when we've said the canonical class is non-zero, for a flop we'd say canonical class is 0 against contracted curves by making the condition kx gamma I equals 0, that's an equals, and correspondingly on the other side, also kx plus, well, we haven't got any notation here, but you can imagine the contracted curves gamma I plus also equals 0. Now, the reason I mention that is because you might not even believe this kind of setup can exist. These are threefolds, and you're not contracting divisors as you normally would. You're contracting curves, and that's slightly implausible. If you work in smooth threefolds, then this doesn't happen, except in this picture. So, as an example of a flop. So just to get a feel for the kind of set theory of the picture, if I write myself here P1 cross P1, so this is P1 cross P1, and then take the cone on this. So this is the cone on P1 cross P1. Well, that's easy enough. I can describe this in equations. If this P1 is x to y and this one is u to v, then the cone could be xv is equal to yu sitting inside C4. So that's that picture there. And the origin is, of course, a singular point to that because there's no linear terms there.
Come on, they're not the same xy.
They're not the same xy. Yeah. Good. That's absolutely right. Okay, there's no option. I'll do the exercise. Let's embed this inside P3 in the usual way. So these guys map to x, u, map to x, u, x, v, y, u, y, v. And so the equation inside there is in variables x0, x1, x2, x3 here is, well, xu times yv is the same as xv times yu, of course. So x0, x3 is equal to x1, x2. And now just treat that as coordinates in C4. So here is x0, x3 is equal to x1, x2 in C4. Thanks. And so this comes with these two families of planes. There's a family of planes that works that way, and a family of planes that works this way. You can kind of see them in this book-like picture. Let me just draw one of these. And you can see these pages of planes moving there. And now, if I take these systems of planes here are fixed; they all pass through the origin. And if I release them by blowing up these planes, so blow up a plane. So here I'm seeing family of planes. Then this P1 of family of planes will be separated out into a kind of disjoint one-parameter family of planes. This will be a little exceptional P1 here. P1, which contracts down to the origin. Now, we could do this in coordinates, but I don't want to do this in coordinates just yet. We'll see something. We'll see how to do it much, in a more systematic way in a moment. But I just want to get this feeling that it's certainly possible to have a moving family of planes. Let me use my plane here. A moving family of planes here, which are pinned down at a point, and then just to free that up so that they move in a family. Well, that was one family of planes, and there's a second family of planes here I could do the same job too. So in other words, a picture like this, where I'm contracting just a curve on each side, is not unreasonable. It's something that's sort of just sitting there in the middle of straightforward, basically undergraduate geometry. But now I want to do the thing kind of more systematically in coordinates. You could do it for that as well. So I have 3 examples, and this is the first. Chapter 2. Chapters 2, 3, and 4. So the title was Flips and C-star actions and diptychs. The diptychs will come last, but now I want to use C-star actions to define flips. So I'm going to let C-star act on C4. And so the C4 here has coordinates x, y, u, and v. And C-star here is acting, so if I have a lambda in there, then lambda is acting on this x, y, u, and v just by, and this is something I'm choosing, lambda squared x, lambda y, lambda inverse u, and lambda inverse v. So if you like, there's a kind of power of 1 there, lambda to the 1, and I'm just going to use these exponents as a shorthand. So I say this action is 2, 1, minus 1, minus 1. That's just the exponents, and it's just to make writing this thing sort of more quick. So what is C4 divided by this action? So C4 is affine, and so you think the reasonable thing to do is to write down the invariant functions in x, y, u, and v, and that's fine. So since C4 is affine, Mumford geometric invariant theory, theorem 1.1, says that, well, not the orbit space. I don't want to get into the details of GIT, but just to be honest, I don't want to write the orbit space, which this notation seems to indicate, but the categorical quotient. But anyway, it's the quotient that I want. We'll see it in a minute. We'll see why it's not an orbit space very easily in a minute. Is a spec of the ring of invariants. So this is just like spec of the ring of invariants is what? C star is the group. So I've got to write down invariant polynomials in x, y, u, and v, and this is just the same as, or just in the same feeling, the same spirit as the finite quotients we were talking about. So, well, you can probably do this exercise as fast as I can. For instance, if I take x and u squared, then multiplying it by lambda will pick up a lambda squared here and 2 lots of lambda inverse. So that will be an invariant function. So get a spec of x u squared is an invariant function. And now you can see lots of others, right? I mean, x uv. That, again, the lambdas come out with weight 0. They all cancel when you work that out. So x uv, x v squared. And then there's some invariance with y, so y times u, again, y times u, they'll pick up lambda to the plus 1 and lambda to the minus 1, which will cancel. So y times u and y times v. And you can think about it for a moment. That generates all the invariants. So just as we did for the little z mod 2 quotient singularity, I'm going to rewrite this with generating relations. So this is isomorphic to spec of C. So there's, I'll give these slightly different names, x0, x1, x2, for those invariants that involve x, and y0, y1, for those invariants that involve y, and now I've got to find out the relations between them, and it's the same game as before. I'm sure you've done lots of exercise in this. xu squared times xv squared is this middle one, xuv all squared. So in other words, x0 times, I'm going to write some minus of matrix, x0 times x2 is x1 squared. And well, let me say the answer, I'm sure you can work this out. It's probably jolly familiar. full stop. So that's, you know, you may or may not recognize these equations. If you do, then you might recognize this as the cone on the surface F1, and it's a linear embedding inside P. How many variables F5 inside P4? So that's a cone sitting inside C5 with coordinates x0, x1, x2, y0, and y1. Well, you might recognise that. It doesn't matter whether you do or you don't. But you know, if you do, then it feels a little bit like this picture here. There's a family of planes that you could think about kind of freeing up at the origin. That's fine. That sort of helps think about the geometry. But I want to do this sort of slightly more coldly. Let me just think about this group action at the moment. So that's by the by. So consider this C4 maps to this quotient sitting inside C5. So C4 mod C star sitting inside C5. Again, these are just perfectly harmless equations. You could find out what the singular locus is and so on. And singular locus is, again, just the origin. So sitting inside here is the origin. And what maps to it, so if this is the quotient map F, then F inverse of 0 sitting inside here is, well, you just have to write these 5 monomials equal 0 and solve them. So this is equal to xu squared equals xu v equals, and all the others down to y v equals 0. So that's not very clear. Equals 0. Well, of course you can solve those. That's the same as the xy plane union the uv plane. Every one of those monomials has either an x, well, has both an x or a y and a u or a v. This is the same picture as Miles was drawing, so in a sketch. Here's C4. So here is, and just reduce the dimension a little. This horizontal axis is meant to be the plane of the xy coordinates, and up here is the plane of the uv coordinates. And all of that lot is being contracted down to the origin. So this all goes to the origin inside this cone. So that's, you know, there's lots and lots of group orbits in that, so that's why this isn't an orbit space. Whereas if you move off the origin, you'll see there are nice closed group orbits away from that locus. So the problem here is the usual problem of projective space, that you know, the origin here is in the closure of many, many orbits, and you could solve this problem just by deleting the origin. So origin is in the closure of many orbits. So they all get contracted to the same point. So they are contracted by invariant functions. To the same point. So of course you know this point, and you know this kind of rhetorical point that you know, one cure is just delete the origin. Delete the origin from C4. But that's not the cure that I'm going to do. That's the cure you do for ordinary projective space. But here I want to do something slightly different. So we don't do this. We could, and it makes perfectly good sense, and it would fit in the picture and so on, but we don't. Instead, what I'm going to do is I'm going to do one of two different things. I'm either going to remove the entire xy plane, which as a part of that process does remove the origin, so that's nice, or I'm going to remove the entire uv plane. And those two choices will give the two sides of this flip that I'm talking about. So let me do that. So this is slightly pedestrian perhaps, but if we can get this right, then when we start throwing in equations, it's going to be much happier. So let me consider instead C4 without, and I want to remove x equals y equals 0. And then I want to divide this by C star. Well, that's fine, we can do that. The only slight problem here is that this is not an affine variety, as kind of Hartshorne exercise 1 says. So this is not an affine variety. So that simple thing of just computing invariance isn't going to compute the quotient. But that's okay. Mumford tells you what to do. So Mumford says, you might like Dolgachev's explanation of this. He writes very nice chapters on this in his book on invariant theory. Or Dolgachev's book. Do 3 steps. So first of all, cover it by C star invariant affines. So step 1 is cover C4 without x equals y equals 0 by C star invariant affines. Two, now those are affines with the C star action, so you can take the invariance. So quotient of those affines. Take the quotient of those affines using invariant functions. And then 3, glue it all together. Glue together. Well, I'm not going to talk about the glue together. That's really what I was saying right at the beginning, is when you do projective space, you define it as affine patches and then you say glue together. But everything's written in the same function, so there's nothing to say. It's kind of automatically gluing itself together. Okay, no problem. This is easy, so we'll just run through this calculation. Perfectly simple invariant theory calculation, and basically nothing can go wrong, I think. So, what could possibly go wrong? So I'm going to give this a name. So, uy, the open set, where y is non-zero. So I'm being careful here. I'm not just saying y equals 1, but I'll get lazy soon enough. So this is, it's affine, and it's affine because it's spec of something, which I can write down. It's x, y, u, v, and, well, I can write 1 over y there, because y is non-zero. So uy divided by c star is the invariance of that, x, y, u, v, 1 over y invariant. And this is just the same game as we were playing before, so I can write them down. If you're doing this in your head, you might do this a little more quickly than I am. I'm going to do a slightly unthinking thing. Certainly every invariant I wrote down before is still invariant. So, well, they've disappeared now, but we can calculate them. xu squared, xuv, xv squared, yu, yv, they are all still invariant. But this is a very cool thing now that y had weight 1, so 1 over y has weight minus 1. When I hit it with lambda, I'll pull out a lambda in the denominator. So if I write x over y squared, that is also invariant. Yes, that's right. And now I sort of, look at the problem again. It's a simple enough thing. And notice that this, for instance, is x over y squared times, and, well, if I multiply it by y, u all squared. This first invariant is a product of other things among the invariants. So I don't actually need him as a generator here, because I already own him as a product of other things. So that's also true for both of these other two factors with x. So these are not needed, not necessary, as minimal generators. So in fact, let me just write down the answer a bit more clearly. This is just spec of, let me just write down who is needed. I only need yu, I only need yv, and this one x over y squared. So that spec of something or other, well, there's no polynomial relations among those, so this is just isomorphic to C3. Nice. That's meant to have a map down to this quotient, so let's just have a quick look at that map. So uy mod c star maps to the quotient C4. Mod c star takes, maybe if I give these some names, I call this U0, U1, and U2. This takes U0, U1, U2, 2. And now, well, I've just gone through all this work of crossing out these generators. Actually, this is expressed in those generators, so I have to work out what is this as an expression in terms of these three. Well, I've just written it down there. It's U1 squared, U0 squared, U2, U0, U1, U2, U1 squared, U2, and then U0, U1, U2. No, just U0, U1. So in other words, I've expressed the original invariance in terms of these U's. And what you see there is, this is a copy of C3, and inside it is the U2 axis. I think everyone there is divisible by U0 or U1. So the U2 axis here gets contracted to the origin. So I am contracting exactly one curve there. Well, that's fine. Of course, I've got to do this for every, for a whole cover, and I've only chosen one affine subset of this. So let me do it for the other. So also ux is C4 without x equals 0, and okay, so we don't have any choice. We've just got to calculate this. So ux divided by c star is, again, the invariance from before, which is xu squared, xuv, xv squared, yu, and yv. Those are the invariants we already have before we allow x into the denominator, but then also y squared over x. And again, write it as generating relations. If you've done the exercise, I'm sure you have, of a half 111 that Miles probably talked about, then you probably already recognize this. If I call these V0, V1, V2, V3, V4, V5, the relations are things like V0, V2 is V1 squared. Well, we already wrote this down. V0, V2 is V1 squared, V3, V4, V3, V4, V5, 2 by 2 minors of that. So in other words, this is, without really thinking about why, this is the affine singularity half of 111. Again, we could find out which part of this. Hello? C3. Thank you very much indeed. You're absolutely right. Thanks. So, you know, again, you can do the exercise of how does this map to the quotient, what's the preimage of the origin. Let me just tell you the thing all in one go. So gluing these together gives, here is some big variety. It's in two affine patches, which I'm not indicating. There's a little half 111 singularity lying on this axis, which is contracted. So this is a copy of P1. And this is, the P1 is contracted down to the origin. To the origin of the quotient. Yeah, that's. It's be good to do that to see where the half is coming from. Yeah. That was one half of the picture. Let me just state the other half. The other half will be non-singular threefold, given by C4 without u equals v equals 0 divided by C star. Again, there's two patches there you have to calculate, and so on. And there's a single P1 there, which is contracting. Right, which I want to calculate a bit of now. Let me say it very quickly. I'd like to calculate the canonical class. So, you know, I said I want to go through it, checking everything. Well, I haven't really said, but it's possible Mars has that this is a terminal threefold singularity. And everything else is smooth. So these varieties have terminal singularities. And I want to calculate the canonical class. So let's just, I can do that on the right-hand side more easily. So check the right-hand side. Okay, let me, you know, let me start getting lazy. My projective geometry. I just say u is not 0, then the quotient is equal to spec of. So in here is spec. Again, we can afford to skip that. It's I think right at the beginning I gave these things names. Let me just remind you of these names. This was x0, x1, x2, y0, y1. And then an extra variable there, which was the coordinate along that P1, 2. So here I also have x0, x1, x2, y0, y1. And then u is non-zero, so I can write v over u. And let me give this a name, A. And the other patch, so the quotient, is equal to x0, x1, x2, y0, y1, and u over v, which I'll call b. If you like, that's the answers. And to calculate the canonical class, I can do this with a three form. So I calculate kx plus times gamma. Gamma is the contracted curve on this side over here. So let me, well, I've been calling him gamma plus, so why don't I continue to call him gamma plus. As follows. These rings aren't as complicated as they look. These are in fact all C3s, so I don't need V's. I can put in any V's by using products with A. And I can put in any U's here with products with B. So each of these is C3. And so I'm going to write a differential form. So on the affine patch, where U is non-zero, I can write a differential form. I'm C3 with these three variables, so I can just write dx0 wedge dy0 wedge dA. That's a regular differential form. It has no zeros or poles, so the divisor of that is nothing at all. has divisor of omega is nothing at all, that's fine, but now I have to look at it on the other affine patch and see whether it picks up any zeros or poles. So calculate omega on V is non-zero. It's not a big deal. I mean, I'm sure that you can see how to do this, but I'll write down the relations I know. So this is what I was saying. I crossed out x2 because it's a product of x naught and a. I crossed out y naught and y1 because it's already a product. I already own it, and I know that b is 1 over a. So omega is what's x naught? Well, if I rearrange this a little bit, it's d of x2b squared wedge d of y1b wedge d of 1 over b. So I'll leave you to differentiate that. This is minus b, actually, yes, minus dx2 wedge dy1 wedge db. So canonical class of x plus is the zeros and poles of this differential form omega. So it's b equals 0. And, b equals 0 is, in one of these affine patches, is this nice transverse plane to gamma plus. So kx plus times gamma plus is equal to 1, which, as claimed, is equal to 0. So you can check. I've done the slightly easier one, that kx of gamma is equal to minus a half, which is less than 0 on x. We can talk about how to do that later if you like. It's a tiny bit more fiddly because of the quotient singularity, but that's okay. Okay, so that was the first kind of easy example, and that's good. So I've got 20 minutes to do slightly harder examples. Ah, very good. Yes, yes. Thank you. So this flip is called Francia flip. Francia flip. So you can go and look at Francia's paper, which is sometime in the early 80s, I think. This is all done in kind of entirely in well-explained, Hartshorne-like classical algebraic geometry, normal bundles and all the rest of it. So it's an example of a toric flip. I'm not going to explain toric geometry, but if you know toric geometry, let me just say this is take the sigma is the cone. Is this cone here 1 0 0 0 0 1 0 minus 1 0 1 2 1 in n is Z3, so that's a cone, and let x be equal to the toric variety of, I'm going to have to divide this up in two ways, that division and x plus be the toric variety of the other division. And actually, to be honest, if I was going to try and calculate this kx plus gamma is minus half, I think I'd much prefer to do it in this language. It's jolly straightforward in toric geometry, but perfectly possible in coordinates as we've done. So we started with C star acting on an affine space C4. I want to do the same now with having C star act not on C4, but act on a hypersurface, and then, in the end, acting on a diptych variety. Next, do C star acting on a hypersurface, so some f equals 0 in C5, and then finally on a diptych. And finally on a diptych. But if you can do this Francia flip, then you're in good, very, very good shape to do anything else. Maybe I don't even need to explain those things. So I think I'm up to chapter 3, which is this next example. So I'll consider now C star acting on a variety V in C5. So C5's got coordinates x1, x2, x3, y1, and y2, where V is some f equals 0, and I'm going to specify this f as being rearranged x1, y1 is equal to x2 squared minus x3 squared. And then possibly plus some other terms, but I'm not going to worry too much about this. So for the Francia flip, I had this shorthand 2, 1, minus 1, minus 1, just to indicate what the action is. I'm going to tell you what the action is, and then have a shorthand. So by lambda acting on x1, x2, x3, y1, y2 is I want lambda cubed on x1, and then just lambdas on x2 and x3, and then lambda inverses on the y's.
So it's intentional that y2 is not in the equation?
It's not, but yeah, that's right, that's right. There'll be other terms there with y2. Thanks. Shorthand. I write 3, 1, 1, minus 1, minus 1. That bit you probably guessed. And then a very clear semicolon. I want to say that the equation had better be invariant in this group action, so it better be homogeneous with respect to these weights. And let me just check that. x1, y1 has weight 3 minus 1 is 2. So the equation has weight 2. So that's the degree of f, the weighted degree of f. And these each have degree 2. And what I mean here is you can throw in lots of other stuff with degree 2 as well. It's meant to be a polynomial, and you can write infinitely things there if you like. But that's what I want. And now this game is exactly the same. I can take a quotient, and I can take quotients with small pieces of this space cut out. More or less, everything is the same, just this equation adds very slight little technicalities to it and slightly interesting additional things. So I won't go into full details of this calculation, but let me compute. So take quotients again, as before. So I'll just do one piece. So let me consider this set where x1 is non-zero. So this is, and so you know, we were writing down invariants, and we could do exactly the same. And it's a very good exercise to try that. It's just a little bit fiddly because there's quite a lot of them. So again, now I want to start getting lazy. So I want to say, i.e. x1 is equal to 1, because I can use the group action to scale it. But I do have to remember that this 1 here has a little stabilizer inside the group action. So, but remember that Z mod 3 inside C star, so the third roots of unity, stabilize x1 equals 1. So in other words, normally in projective space when you say x1 equals 1, you're just taking a slice of a group action. And here I'm not quite managing to do that. There's a little bit of group action still left. But that's good. If I just overlook that point, if I set x1 equals 1, then this is an equation for y1, so I can remove it. So with x1 equals 1, the polynomial f eliminates y1, because it's a function of other things. And so I could say it like this. I could say ux1 divided by c star is therefore, well, x1 is 1, y1's gone, so there's only 3 variables left, c3 with coordinates x2, x3, and y. Something's gone wrong. No, nothing's gone wrong. Nothing's gone wrong at all. This is great. It's just kind of nervousness in front of an equation. That's approximately all that's left, kind of doing this invariant theory more or less in one's head, except there's this little Z3 still acting. So Z3 still acts here. And it acts in the same way as C star acts. So the Z3 is just complex numbers. It happens to be cube roots of unity, but they still act by lambda, lambda, and lambda to minus 1. So it's acting by 1, 1, and then minus 1. So in other words, this patch is a copy of a third of 1, 1, well, that's minus 1, 1, 3, so I can call it 2, which again is a terminal singularity. So that's good. So what we have here is there was the quotient, which we didn't bother to calculate. Here's, again, the origin will be a singular point of that. Here's x1. We've found one of the patches. There's other calculations to do, but we found one patch. So somewhere on here there's a little singular point, a third of 1, 1, 2. I haven't yet calculated what's contracted to the origin, but the equations are all sitting here in front of us. I can perfectly well do that. And what I'll find is there are 2 P1s. So gamma 1 union gamma 2 equals P1 union P1 contracted to the origin. We could go through all that calculation. It would be very, very similar to the last one. Let me just try to say a slightly easier way of seeing it, though. That calculation is identical, apart from the carrying the equation through it, to the previous calculation. So perhaps a slightly easier way to see the whole picture rather than calculating honestly, carrying the equation, is just forget the equation for a moment, is to forget the equation. And we'll get a flip diagram, so a flip-like picture, but of 4 folds, of toric 4 folds. It looks like this. So here is some great big toric 4-fold contracting down to some other toric 4-fold. And what's getting contracted here is, just as in the Francia flip, it's the space whose coordinates are the positive weighted variables here. So this is a P, well, 3, 1, 1. Those are the weights on the x's with coordinates x1, x2, x3 is contracted down to 0 now. So that's the same calculation as Francia. And on the other side, we have a toric x plus contracting down to y, and sitting inside here is a P1 with coordinates y1 and y2, which contracts down to the origin as well. It's going to have to contract in a roundabout way. So that's just that's forgetting the equation. That's just doing exactly the same as Francia. And now I want to worry about how does the equation cut out curves inside these 2 exceptional loci. Well, this thing here is y1 equals y2 equals 0, whereas this here is x1 equals x2 equals x3 equals 0. And if I look at the equation and I set the y's equal 0, well, that term goes. Everyone else here will have to go as well, because they'd better have some y's in them as well. And I'll just be left with this x2 squared equals x3 squared. So sitting inside here is x2 squared equals x3 squared, which is 2 lines. 2 lines that pass through the third point, which is the same as the third point we calculated there. And over here, the equation, when I set the x is equal 0, well, every single term has an x in it. So this P1 is also contained inside the x plus there.
And then sorry about
No, sure.
how can I make x from x to a toric fourfold? So how can I relate the toric fourfold and x?
Yeah, very good. Very good. That's right. So this toric fourfold here is just the toric guy. I'll forget the equation for a minute. Is C5, and then I've removed x1 equals x2 equals x3 equals 0 and divided by C star. So that's a fourfold, and you'd calculate it with 3 affine patches where each of these is non-zero in turn, just as last time. And then in each of those affine patches, then I write this equation. But of course the affine patches are going to look, you know, what the coordinates in an affine patch are going to be. They're going to be things like, let me try and say, if x2 was non-zero, we'd have things like x1 over x2 cubed, x3 over x2, x2y1, x2y2. So those would be coordinates on this patch. And of course, I can, just as in projective geometry, I can write this equation in these variables by dividing through by some x3s. And then I'm recombining them on this projective space. Yeah, no, that's exactly the point. You've got the right thing. I mean, there's certainly a little bit of calculation left to do. I'm not saying that I've sort of explained all that in one go. So the result is, here's the threefold, which is cut out by a single equation in toric fourfold with, I see I've drawn that more or less, with a third singularity sitting on that, contracts to some y, which we didn't have to calculate, and coming out on the other side is a non-singular threefold x plus with a P1 contracting down. So these are each copies of P1. These things are all general features of flips that you can see in papers of all sorts of people, Mori and Kolar, Shukurov, that, for instance, singularities over on the right-hand side are better than singularities on the left-hand side, aren't all. Or the number of curves that you're contracting, there's going to be more curves on the left than on the right, or greater than or equal to. But still, these are just examples. I see. So 5 minutes to explain a diptych. So this was just the same as the previous calculation, just including one equation. Now I want to do Miles's first example of a diptych and build flips out of that. So diptychs give flips. So the first example, so the easy example with this, Miles had a general A there, but I'll set A equals 1 just to keep life a little bit easier. It looked like this. That was the left-hand side of the diptych. The right-hand side looked like this, 1, 0, Lm. Well, that's just kind of force of habit writing down these diptych pictures. What it really meant was, well, the way we're going to use it is just by writing down the equations. x1a plus m. This is exactly what Miles wrote. Is b plus x naught L. So this is my diptych V. or VABLM. This one. Exactly, yes, thank you. Okay, so I say that I'm going to, this is some variety. Again, I'll put C star action on it, take the quotients, that will give a flip. There's a little intermediate step here, which is called regular pullback. Let U and T be two new variables and set A is U to the alpha, B is U to beta, L is T to the lambda, and M is T to the mu. Positive integers alpha, beta, lambda, mu. The result is a VUT. So this was called VABLM. And now just trade in the ABLM for these things in U and T, which is a sixfold with, that was a sixfold, this is a fourfold, thanks. A fourfold with, well, here we had 4 independent C star actions, but I'm killing some of them, well, depends exactly what I do, with 3 C star actions. In other words, this fourfold V has a lot of C star actions, and some of them are going to be appropriate for flips. So I choose one which will give a flip, whose quotients give a flip. So I just better tell you weights of the variables, that's all. The C star action is given by x0, x1, y0, y1, u, and t. I start off by choosing that u and t have those weights, and then I'm going to do everything else to make this lot all homogeneous, which is not so difficult. M has weight is mu because it's t to mu, so A has weight 0, so x1 had better have weight mu, and so on. I'll just fill these in. Minus mu and lambda plus mu. So let me just say that this was a choice. Those two was a choice. These were determined by the equations. Determined by the homogeneity of the equations. Okay. To make the quotients, I'll do this again in 2 steps. I'll first just forget the equations. I only have 2 equations here, but I'll forget them. I'll do a toric thing just by dividing C6 by the C star action. Gives a 5-fold flip diagram. And it's going to be exactly the same. The positively weighted variables here will give coordinates on the exceptional locus on one side, and the negatively weighted ones will give coordinates on the other side. Which is x. There's a slightly awkward thing here. One of them got weight 0. So let me pull out this A1 with coordinate u, because he's got weight 0. Contracts to some y cross A1u. So u is just an invariant in everything. Cross A1u. And what's contracted inside here is the positive weights, which are p of mu, lambda plus mu, and 1. That's x1, y1, t, cross this A1. And what's contracted in here is the negative weights, which is p of lambda mu cross A1, where these coordinates are x0 and y0. So I haven't put the equation in yet, But that's the kind of ambient space for this flip. Setting the equations equals 0 cuts out the threefold. Sorry, I'll just go on for another 2 minutes and then I will stop. In other words, sitting inside this picture on the left is an x, sitting inside here is an x plus. And really to understand it, I just want to understand it in the neighbourhood of the exceptional locus. So I'm going to work out what happens when I write the equations x, but I set x naught equals y naught equals 0. So, well, I've got them there. X naught equals y naught equals 0 gives me x is x1a, which is u to the alpha, plus m, which is t to the mu, is equal to, there's x naughts and y naughts all over the place there. Maybe I've got something slightly wrong, but is that sitting inside this exceptional locus? In other words, at least just to compute the set here, u is 0, and if u is 0, then t is 0, i.e. u equals t equals 0. So in other words, the exceptional locus on the left is, I've set u as 0, so that's killed this A1. I've set t as 0, so it's a p of mu. I think this is lambda plus mu, isn't it? Lambda plus mu. Sorry? Thank you. So this is contracting a P1, and on the right, well, you can do the similar exercise. It's a P1 of lambda mu is contracted. You can see the singularities and so on. I don't quite have time, but that's a relatively easy calculation. Let me just say what the kind of punchline of all this is. That's a simple thing. Miles was making examples that had many variables down the sides here. Well, we can allow that. That's fine. That will just make these ambient spaces much, much bigger. But we'll have lots and lots of equations which would kill all those variables. In the end, all we'll be left with is this little portion, these two variables here, a P1 on x to k, y, l, the top variables there, and this little P1 here on x0 and y0. So this will be the exceptional locus on the left-hand side, and this will be the exceptional locus on the right-hand side. And then all the other calculations, like the singularities, the canonical class, and so on, we can do. The critical thing here was that the weights up here were positive weights, and the weights down here were negative weights. That's one place where this choice of u and t helped. There are other reasons as well. Once you do that, this calculation works on the simple diptych, and it works on any diptych at all. So I'll talk more about that next time. Thanks very much.